If you're building or renovating a device that runs on high voltages, if you're trying to fix it or trying to test a new piece of circuitry out, what you often don't want to do is put the full mains voltage on it. So a piece of electronic equipment or a valve radio is a good example. Now, a device that's really very easy to set up is something called a variac, and that's an auto transformer. Basically what it is, it's a transformer with a single winding, and what you do is, because of the effect of inductance on a winding, if you actually tap a lead any particular point in that single winding, you're going to get different voltages at that point. That's a very short explanation of how an auto transformer works. There's a lot more to it, but that can be for another video. But basically the point to understand is you have a coil of wire, and you'll have a tap off that coil of wire, and anywhere that tap happens to be will give you a different voltage. Why is that useful to us? Well, it means if we've got a coil of wire that we can move the tap up and down with a control knob of some sort, then we're able to give different levels of voltages. And there is actually a device that does that for us that we can buy off the shelf, which is very easy. I mean, you can make one of these, but it requires a lot of copper wire and lots and lots of windings. It's easier just to buy one ready wound. So that's what this item is. This is known as a variac. This particular model is from RS Electronics, but you can get them in numerous different places. Now, this particular model will actually handle up to 15 amps, but I'm never going to be using it for that level of current, but it's capable of handling that. So it's quite a bulky thing. The other thing you need with one of these, though, is although you're actually being able to adjust the voltage, you are up against a problem of safety here, because no matter what the AC voltage is, if for example you're at 240 volts and you're using an oscilloscope or some measuring device and it's earthed, then as soon as you try and probe anything, current is going to go through the earth of your device and it'll probably blow up your oscilloscope. So to avoid that happening, the other nice feature to add on to when you're building something to work on valve radios, etc., is something called an isolation transformer. What I'm describing here is the joining of both the isolation transformer and the variac inside one box. And what that means is this will give us the variable voltage control, and then between this and the mains we have an isolation transformer, and that will provide us safety. And I'll explain how that works in a minute. But just to give you an idea, what you need to do, of course, is you need to build some kind of a box to hold both of those units. So I'm just going to quickly go through some of the stages I went through to build a box to do that, just to show you it's not a difficult thing. So the first thing I did was I cut out a template. I cut that out with a coping saw, and that diameter there was exactly the same diameter as the variac here. So I cut that out and then placed that over the top of the variac, and you notice the 4 holes, I lined those holes up with the 4 lug holes in the variac. Now the idea here is, I thought, something very easy which you can use yourself. It's a very easy idea, is to get some studded rod. So what I did is I purchased some studded rod with some nuts and bolts, you know, and the finishing nuts on the end, with the rounded nuts on the end to make it look a little bit nice. And I slotted those through. Now, the reason I did this was I'm then able to put nuts in between, and you get this effect. So what I've done, as you can see, in the middle of those studded rods, you'll see 2 nuts, 2 locking nuts. So the 2 locking nuts will hold the base of the variac, and the top of the variac, you see, is sticking through the end plate there. And you'll see that I've got the finished nuts on the top. Now what I also did with those finished nuts is I put a plastic, you can buy plastic nut cover for those as well, which I bought those and made it look a little bit nicer. Now the gap underneath then is for the isolation transformer. Isolation transformers can be all different sizes depending on how much ampage you want them to be able to handle. So for example, what I have got at the moment is a small isolation transformer which will handle up to about 1 amp. But for the devices I'm going to be working on, I won't be pulling any more than 1 amp. So it's okay. I mean, later on, if I want to work on devices that pull much heavier current, then all I need to do, if you can see here, is extend those studded rods, buy some longer ones in other words, and then I can fit in any size isolation transformer I like. I mean, the widths of the isolator are generally the same. It's just the height of them because there's extra windings on them. That's good because it means if I want to extend this, I can pull out the old isolation transformer and put in the bigger one later if I want to. So this is what it looks like when the isolation transformer is fitted. So now I've wired everything up. I'll show you how all this gets wired up in a moment. Now you can see the isolation transformer at the bottom there. It's got its own lugs against the wood end panel. Now I just screwed those down using quite thick hardboard. That gave me plenty of strength. And with the studded rods there, you can see everything's kept nicely in place. Let me just go through the isolation transformer and why it's important and how we use it and what it actually is. Okay, I'm just drawing this out very roughly so you can see the general idea of what's going on. So there's three images there. The first one on the left shows what happens when you don't have an isolation transformer. The top is the live. Underneath with a round circle that says 240 volts AC, that's supposed to be the mains there, the mains voltage. Then underneath you've got the neutral wire. And then of course you can see that the neutral is connected to the earth. Well, that's the case with all mains. If you are on the neutral side, on the blue wire, I mean, I don't advise anyone ever touching the blue wire, but basically if you touch the blue wire at the power socket, you're not going to get electrocuted. Don't do it anyway, but if your electrics have been set up correctly by your electrician, then your neutral wire will be at exactly the same potential as the earth. So you can't get electrocuted because you're at earth potential. So there's no way any current can flow if you're at the same potential as what the earth is. Yeah? That's the neutral. The neutral is connected to the earth for that very reason, to make sure that the neutral side is always at earth, because then you're at earth and so no current can flow. The point is, if you touch the live wire, you are at earth potential. Instead of the current going back and forth, it's going to travel through you to get to earth. You're going to get electrocuted in that in that scenario. Using a person here, but this could be an oscilloscope. So if you've got a probe or an oscilloscope and you're probing something and the other side of the oscilloscope is earth, you put the earth against one side, then you can actually blow the whole unit up because you're sending all that current through the actual oscilloscope. So you want to be able to isolate yourself and any equipment that you want to use when you're testing or fixing units. How do you do that? Well, this is where the isolation transformer comes in. With the isolation transformer, what you've got is another coil of wire, and you're using the Faraday effect, if you like. The fact that if you have two coils of wire next to each other, when the current is flowing back and forth, it produces a potential on the winding, and that produces an opposite potential on the secondary winding. I won't go in all the details of this. If you want to look that up, just look up how transformers work. But the essence of it is that in terms of protection, it means you've got an isolated circuit here. So the wire that the chap is holding there, and he's smiling, he's not being electrocuted there, the other side, you can see it's not connected to earth. That's the main point. Now, if he was to touch the other side of that lead, the bottom lead, and then he would get electrocuted. This is why you often say when you're dealing with high voltage equipment, if you're using an isolation transformer, but always still put one of your hands in your back pocket so that you could only touch one side of it. There is a chance that you can make a connection to the other side. You're not going to get electrocuted if you're only using one hand. It's very unlikely. So that's a safety measure that's often discussed. We want to be able to protect our equipment more than anything. As an example of testing equipment, let's have a look at this diagram here. Now here, we've got a scope this time. The device under test is now connected via the isolation transformer. That says DUT, device under test. We've got the leads of the oscilloscope probing across the device under test. Now, it means the scope is protected because that whole circuit is isolated from earth. A current can't pass through the scope from the unit. So that means the scope, the actual scope device there, is protected, just like the person was protected, because the actual circuit itself is completely isolated from earth. That's what an isolation transformer can do for you. It can protect your instruments, it can protect you. If you're working with a variac that can change the voltages and everything, you're actually directly connected to the mains. So it's really important, really, that you isolate that. So that's what I did, was to build this box. This box is a variac, really, with an isolation transformer to protect the instruments I'm using and myself. If we look at the details of the variac here, so this is the variac I've purchased. It says enclosed variable transformers installed. This is the general sort of like leaflet you get when you buy that variac I showed you. So there's the diagram of it, drawing of it. And then here is the main wiring diagram. You can see it's just a single coil of wire, and that's exactly what's inside. It's a lot of coils of wire though, not the one shown here. It's many coils of wire, but in essence that's what it is. It's one long length of wire, yeah, but wound many times. And then the E here showing as E, that's a tap. Now you can see that it looks like it can move around. Well, it can. So that tap can move. When you turn the dial, you're turning that arrow up, and that's giving you your different voltages. So you can start from 0 volt at A and all the way move it round to C, and you're at the maximum voltage of the mains voltage. So it's a very basic thing. It's just a whole lump of copper wire, really, just wound many times. So this is the schematic of how you would wire the two units together. On the left hand side there, the variac initially is connected to the mains via A and C. A goes to the live wire, C goes to neutral. This is in the UK. You've got the live wire is the brown wire and the neutral is the blue. I'm not sure what the colour coding is in anywhere else, but that's in the UK. Then on the other side you've got this E, which is this tracking part of it. So the E is where you're turning the knob and you're changing where that tap is going to be along that coil there, and that gives you the different voltages. We connect up the E to one side of the primary of the isolation transformer. So if you follow the E, you'll see on the right hand side another dash box there with the E connected to the primary side, and the other side of that primary coil is connected back to C, which again is the neutral wire, which, remember, the neutral is connected to earth. And then of course you've got the other earth, which is the earth that you see in your power plant. I mean, it's connected to the same place, but it's just that the neutral wire is generally connected either outside the house or out close to the junction box of, maybe if you're sharing your electricity with another house or something. But the earth wire is also there as purely for protection purposes. Yes. So I've included the earth in this setup. The protection earth there is connected to a piece of metal on the variac and another piece of metal on the isolation transformer, the lugs, if you like. So I connected those to the lugs. So if, for example, the live wire was to fall against the lug in the variac, then it'll just earth out because that's connected directly to earth. So then you'd have a short and the thing would blow a fuse or something in the fuse box, as opposed to catching fire. So that's what that earth is for. But you can ignore that in terms of what's actually going on, because you can see on the secondary side of the isolation transformer there is no connection to earth there, and that's your isolation. So then you can see, if you look at the two outputs of the isolation transformer, I've got an AC voltmeter across, which measures the voltage between those 2 points. And then in series, you could select one of 3 ammeters. So I've got 3 ammeters there. And the reason I've done that is if I want to, when I first switch it on with the device under test, I will have the first ammeter, the switch on the high position, which is the ammeter which can handle the highest current. And then if I find when I turn up the voltage I'm not seeing any current, they can switch it back down. So I've got 3 levels there that I can then get a good measure of what the current is. Because what you don't want to do is run that on the ammeter that can only handle a low current, otherwise you're going to damage the ammeter. So instead of doing something sophisticated like some electronic sensor or something, I just did it very simple, used a switch. So I know that when I switch that on, I'm going to have it at the highest setting. So I've got something like a 3 amp meter at the top, a 300 milliamp meter, this next one down, and then the last one is a 50 milliamp meter. So then you just make sure that when you switch it on, it's always at the top position and you can't damage any of your meters. And that's nice because you're able then to measure any ampage between 3 amps down to 50 milliamps or down to 10 milliamps. So that's nice. You've got a feature that you can actually read off the current. So that's how the wiring diagram is. That's how the schematic is. Now, to realise that, you want to wire it all together. So there's the actual wiring diagram, and that's the actual units, how they look when they're in that box. So you got the variac there. I'm showing that as the physical unit. You can see it's really just the same as that schematic, really. I've actually drawn the schematic part of the coil of the variac as an example there. So you can see the variac there is shown in two ways. It's the schematic part drawing of it and the actual variac. E is connected to the isolation transformer. The C is connected to the isolation transformer, and it also connects to the neutral wire, which was the same on the schematic. And also I'm showing, which I didn't show in the schematic, was fuses. So I've got a fuse there of 5 amps in the live wire which goes to the variac. And I've got another fuse. Now these fuses are to protect the units more than for safety reasons, because I don't anticipate ever going beyond 5 amps for the variac. The variac can handle up to 15 amps, but I don't want it going any more, because then obviously the secondary is going to be pulling more current. And also, to be even more sure, on the isolation transformer on one of the output secondary leads, I've also got a 1 amp fuse, which you can see. So if I am drawing more than 1 amp, then that fuse is going to be the first fuse that blows, giving it double safety, if you like, in terms of not damaging the isolation transformer. So the 1 amp fuse protects the isolation transformer, and the 5 amp fuse protects the variac. I'm showing the 3 ammeters again, more or less in the same way as I showed it on the schematic. And then the output is then to your 3-pin socket. So you'll have a 3-pin socket there, which you can plug in any of your units under test, and you're completely isolated from the mains. You're protected, and you can set the voltage to any level you want. So what have I got at the bottom here? I've got danger. Please read instructions carefully before wiring up your own variac. Yeah, because every variac is slightly different. There'll be different ways wiring. Very important that you read it and understand what you're doing before you mess around with mains voltages. Just get a good understanding. If you know what you're doing, you're going to be okay. Incorrect wiring could give you a shock. The variac in this circuit could be very different to other versions. Well, put it this way: if you don't understand how a transformer works, then you shouldn't be messing around with anything at all in terms of mains voltage. Fine to mess around with 12 volt radios and stuff, but not mains voltage. But if you do know how a transformer works, then you know how all of this circuit works, because that's the hardest bit of this circuit. The only thing not intuitive is how transformers work. If you look at my video on power supply, you get an explanation of how transformers work on that. So that could maybe you want to watch that before you watch this again. Once you've wired everything up, before you do anything else, before you connect up your ammeters and everything else, you just want to make sure that everything's working correctly and that the volts. So I've turned it on here now. What I'm testing here is that safety red button there. So it's a red throw button. It's a safety button, and when it's up, it shows the bulb, but it's not actually. And you see when I close that red button, then I can start seeing the voltage. And I'm turning the voltage up now, just checking that it's working. You can go above 240 volts. Yeah, it gets up to 257. That's because the winding is a little bit further on, and it gives you that extra voltage. I put on a temporary ammeter there just to check that the wiring, everything's okay. And you can see here, look, I can actually measure the current that's going through. So I've got 2 very high wattage resistors there, low value. There was quite a high current, even though the voltage was very low. So I was using large wattage resistors there so that I could see a nice swing over on the ammeter. So I was happy that that's working. Then finally I fixed in the 3 ammeters. Now here's the actual finished box with the ammeters in. Just above the 3-pin socket, you'll see I've got a black round switch there. That allows me to select what ammeter I want to use, whether I want to use the one on the far left, which is the 3 amp ammeter. The one next to it is 300 milliamps, and the one next to the voltage meter, which is on the far right, the one next to it is the 50 milliamp ammeter. And you can see that the switch there, you can see it's pointing at the top, then that's the far left, that's 3 amp. So whenever I switch it on, I'll have it in that position first to make sure, you know, I've got plenty on that dial. That it's not going, obviously this thing won't ever go to 3 amps because I'm only ever going to be running an amp through it. So that's kind of gives me that safety margin if I do want to have a bigger isolation transformer later and actually work on units that deliver higher current. I can, because that ammeter will go up to 3 amps. Nice thing about this, of course, if you want to measure devices that you're using, you can actually measure the power really easy. To work out the power of anything, you only need to know how much voltage you've got across it and read off the current, because voltage is joules per coulomb, so it's the amount of joules of energy per coulomb that moves through the circuit. So if you multiply that by the number of coulombs that move per second, you end up with the term joules per second. Now joules per second is watts, so that gives you your power, and that's what we measure. And we say a 240 watt bulb, we say it burning 240 watts, it's burning 240 joules per second. So that's the amount of energy it's using up. So that means with this, because we can see the current and because we can dial in the voltage, I mean it's not that accurate, to be honest, because you know, it's good enough though to give you a rough idea of how much power something is using, and that's all I want really. I'm going to be working on valve radios and such, so this is ideal for that, and I can get a good estimate of the power it's using. I can see how much current it's drawing, so I can tell if something's wrong straight away. So it's a really very simple thing to build. As long as you understand, like I say, the basics of electricity, and you're okay with that. It's a very simple thing to build, but it's very, very useful. The variac's probably the most expensive unit. You can get them second hand if you get on eBay. They come up on eBay quite a bit second hand, so you can get a bargain. I got that one new. I can't remember how much it cost. I think it was a couple of £100 or something. It wasn't too expensive. The isolation transformer I got second hand. Again, they can be expensive if you buy them new, but I think I got that for £50 or something second hand. They always come up on eBay a lot, so you don't need to spend a lot of money to build this. And that's it. So now I can use this, and I can use this when I'm working on something that's using high voltage. I can work with it knowing I'm safe, and knowing that the oscilloscope that I'm going to measure, what I would do is I will plug the oscilloscope into the mains, so I'm mains earthed on the oscilloscope, and then the unit I'm working on, I will plug it into that 3-pin plug there, shown there at the bottom. I'll plug the unit in there that I'm testing. So this box will only ever be used to test things with. That's what it's there for. It's not used for anything else. I wouldn't be plugging in my hairdryer or anything else in there. Actually, if I plug my hairdryer in there and tried to use that, it would probably blow the fuse straight away, because that can only handle an amp, and I think a hairdryer probably goes beyond an amp in terms of current. So yeah, you only use this when you're testing things like radios or, you know, units that work from the mains, and you want to increase the voltage gradually to protect it in case it's got a short inside. So if something's got a short and you've got a high voltage and you just plug it in with a high voltage, you're going to get an instant high current, and it could just catch fire almost immediately. Whereas if you turn up the voltage slowly, and you've got meters to show you what current, if you see the meter start rising real quick, then you know you've got a short there, and you can quickly back off the voltage, and you save the device, you save it catching fire. I hope you've enjoyed this video. Hopefully it makes sense to you, and I'll catch you on the next video.